Another important concept is the idea of an insulator, a conductor, and what's called a semiconductor. So an insulator, well, from their names, the ideas are they're more important. Here we're looking at electrostatics, so electricity when charges are not moving. So when charges are just standing still. When you look at electrodynamics, you can get what's called insulator. An insulator is a material that does not let electricity flow. It blocks the flow of electricity, so blocks the flow of charges. So when an insulator becomes charged, like our balloon, the charge is going to be on a local part. Like if I charge a part of the balloon with my hair, not all of the balloon is charged, just the part that was in contact. Well, theoretically. Not all the balloon is going to be charged, just a small part of it, the part that was in actual contact with the other surface. So that's because in an insulator, the charges can't just move around and spread everywhere. They have to be localized. A conductor is the other way around. A conductor is a material that can let charges and electricity flow through it. And in fact, a conductor, because of this, you can never have a localized amount of charge in the conductor. They will always spread. So as soon as you charge one bit of a conductor, all of it gets charged. A semiconductor is, well, from its name, it's not perfectly conducting, but also not perfectly isolating. It depends on a lot of its material, and semiconductors are, because of this switching idea, because of their ability to switch behavior, they are really important in computing applications. So when you want to create a switch, and a switch is a very fundamental object in a computer, something like a transistor, for example, semiconductor is what you need. So yeah, so examples of insulators are, I mean, you've met insulators all the time. Most of the material we come into contact with today is going to be insulating: walls, glass, rubber, wood, concrete. Conductor metals, just any metal. Different metals will have different amount of conductance, but they'll generally all conduct. So that's copper, silver, aluminum, iron, even mercury. So semiconductors are things like carbon, silicon, germanium. So they are a particular group of chemical elements that have this. So if you have studied the periodic table, you'll know that there's a group of elements on the periodic table that's called the semiconductors. They lie right between the conductors, so the metals, and the non-metals. So that's why, for example, a lot of computing hardware is using silicon. Yes, Attila.
And what is a superconductor?
So a superconductor is a material where electricity can flow without resistance. So conductors, yes, they let electricity flow, but there is resistance to the flow of electricity in a conductor. So if I put some electricity in a conductor, over time, as it moves, the electrical energy will start to dissipate because you're meeting resistance. And in fact, this resistance is very useful. So for example, incandescent lamps, like old style lamps that have a filament inside of them. So the way they shine is because when you run electricity through that very, very thin filament, the resistance to electricity is so high that the electrical energy transforms into heat, which gives you light. So a superconductor does not resist electricity whatsoever. You put some electricity in it, it will perfectly flow. And that can be very useful. And there's a lot of very interesting properties in them, in that, for example, a superconductor can be constructed in a way, because of its unique properties with electricity, it also has unique properties with magnets. So you can make superconductors levitate and maintain a particular, and not just levitate and not just push away, but levitate at a particular height and not move from it. So lock in place. It's called flux spinning. So superconductors can do a lot of very interesting things, not just transport electricity without any losses. So, yeah. next is the concept of ground. So have you guys ever heard of the idea of something being grounded? So basically you can think of electrical charges as something that, okay, electrical charges will not want to stick together. That's the same electrical charge. So if I charge an object with a lot of positive charge, the positive charges will want to dissipate, will want to move away because they're repulsed from each other. So the Earth, however, is huge. So if I give the Earth some charge, a little bit of charge, it's not going to be charged. The Earth is so big and has a lot of conducting material in it that as soon as the charge goes to the Earth, it just disperses. You can easily transport an infinite amount of charge to the Earth. Well, practically. So to ground something means to connect it in an electrically conducting way to the Earth. And that will always sap away the charges. So if you ground an object, you connect it to the Earth, basically. So in this example, you have a sphere that is uniformly charged, and you separate the charges in the sphere by putting something that is negatively charged on one side. So if we just zoom in here. So we put a little object that's negatively charged on the left side of the sphere. And because it's negatively charged, it's going to pull all the positive charges towards it and push all the negative charges away from it. Now I connect the sphere to the ground. The negative charges are going to go to the ground. They're going to flow to the ground. They want to move away from the other negative charges. But the positive charges can't flow because, well, they're connected. They're hooked. So now if I remove the ground connection from the sphere, I'm just left with a positively charged sphere. So that's one way of using, without actively rubbing in or rubbing out any charges, you can just very easily take away some charges from a metal. Now, polarization is basically having some charges on one end and the opposite charges on the other. So a material that's polarized is a material where the charges are not evenly dispersed everywhere to make it neutral. It's a material that is overall neutral, so it has the same number of positive and negative charges, but they're split. So you have local charges, even though that overall it has no charge. So that's the idea behind a polarized material. Overall, a polarized material has zero net charge. It has the same amount of positive and negative charge, but they are separated to create a polarization. So polarization will generally happen strongly when you're in metals, because in metals, charges can move freely. Well, when something is an insulator, charges can't really move freely. So you can't really cause the separation of charges easily. So an induction is basically charging a conductor, is creating an imbalance of charges in a material that's conductive. That's what inductance means, or induction. So you should note that a lot of this terminology comes from a lot of historical context. So a lot of these things were, although they seem very similar to each other, would have separate names just because historically they were discovered and thought to be separate things. So for example, just to give you one of the ways there is a historical quirk in electricity. So electrons have a negative charge, right? And when you look at a battery, you have a positive end of the battery and a negative end of the battery, and to us, electricity would flow from the positive to the negative, as if something is flowing from what is in excess to what is. So a positive means it has more of something, Negative means it has less of something. In reality, that's actually the opposite. The positive end of the battery has fewer electrons. It wants electrons. The negative end has too many electrons. And that's just because when we first discovered electricity, we didn't know about electrons. We didn't know about how any of this works. So we assumed that it works one way. It turned out it worked complete opposite, but we just kept the names of what does positive and negative mean. So you're going to find a lot of weird things like this in electricity that just come because of some historical accident.